This is 7.1b as in Bravo in college algebra, systems of linear equations in three variables. We're starting on example 2. Hopefully I won't need a video for every example, but anyway, they're using a story problem in order to do this, and there's the table 7.2 here on the screen. So we've got this manufacturer of furniture has three different models of chairs, one called the Anderson, the Blake, and the Colonial. Now the number of hours required for framing for each type of chair is here, and for upholstery and for finishing. So for the Anderson it takes 2 hours to frame, 1 to upholster, and 1 to finish, and all this for the other ones. Alright, the company has 1,500 hours per week. So 15 hours per week for framing, 2,100 hours for upholstery, and 850 hours for framing. Okay, that's how much they have set aside to do each of those, so then they can have an idea of how much it's going to cost in order to make a chair, because they're paying people per hour to make these chairs. So how many of each type of chair can be produced under these conditions? So what we've got is the frame. Let's look at the framing first. The framing says that we are going to take 2 hours times x, and the x represents, the number of Anderson chairs, y will represent the number of Blake chairs, and z will represent the number of Colonial chairs. So 2 hours to frame an Anderson, plus 3 hours to frame a Blake, plus 1 hour to frame a Colonial, and the x and y and the z are the number of chairs, and that should equal the 1,500 hours. So our first equation is going to be, let me get my eraser here, y plus 1z equals 1,500 hours. Okay, to upholster, we're going to take those numbers right there, which will be 1x plus 2y plus 3z equals 2,100. And then that's how much to frame. 1x plus 2y plus, 1/2, let's use 0.5, equals 850 hours. There's our system of equations there. And we can get rid of everything else because we are just solving for this system here. Now, if you remember in the last video, we had determined that we need to do these so that we've got 1x, y, z, 1y, z, and then a z. Which means this number has to be a 1, this has to be a 1, this goes away, and the x and the y down here go away. So that's what we're looking for. So, what are we going to do? Well, I would suggest just flipping these two around. So, remember what we had said. You can do that, and that takes care of one step here of getting the x to have the number 1 on it. Because it already does, we just switch things around. And then our bottom one, obviously, we didn't do anything to. Now, you could have left that 0.5 in a fraction if you want. Doesn't really matter, but it just kind of makes it easier. Okay, so since, we'll go ahead and lock this one because we have our 1 there. Okay, so that's good. But we need to get rid of this here. So we're going to multiply this whole thing by -2 so that when we add it to that, our x's go away. So I'm just going to put my -2 up here. Let's do it in red. So -2x minus 4y minus 6z equals, don't have enough room there, negative 4,200. Okay, so I'm going to add that to our 2x plus 3y plus 1z equals 1,500. That goes away. That gives me negative y minus 5z equals negative 2,700. Okay, so let's go ahead and write this as we have it right now, and let's do it in blue. So we have our 1x plus 2y, what we have locked here. This is our new second row. And then our third row has had nothing done to it. Okay. Now, we need to make that positive. In order to make that positive, we multiply the entire thing by a negative 1. Okay? And what that does is it changes that to a positive, that to a positive, and that to a positive. Okay, so far we've done three things. We made that a positive 1, we got rid of that, and we made that a positive 1. So this is now locked, since it's where we want, and that's locked. Okay? So now what we need to do is we need to get rid of this and rid of this. Well, how can we get rid of this? We have to use this equation because it's the only one left with a y value. Okay, so we're going to multiply this top here by negative 1 and add it to that. Okay? Or, now that I look at it, another option is to multiply this whole thing by a negative 1, and that will be added to that, and we can get our answer. But let's do what I said first. Doesn't really matter which one you do, but let's just do that. And that gives me negative 1x minus 2y minus 3z equals negative 2,100, and we're adding it to this, the one that we're changing. Okay, add those up, we get 0. Whoa, we add those up and we get 0. That's awesome. And we have negative 3 plus 0.5. Add these up and we get negative 1250, and we divide that by 2.5, and we get z equals 500. Whoa, that was easy. Because these two both canceled out here, we were able to find our z real quick and easy. So basically, this is our locked version of z. Alright, so now that we know z is 500, then we can take our 500, plug it into here because this is locked, plug it in right here, solve for y. Once we find y and we have z is 500, then we plug the y and z here and solve for our x. And that's, again, how you do these. Okay, so I want to give you a little bit of a pictorial graph on pretty much what's going on with these three-dimensional objects, because, you know, when we're dealing with x, okay, like 2x plus 5 equals 0. We have one variable, which means it's one-dimensional. It's a line, okay? And all that you have with a line is the length of the line. Okay? When we have an x and a y, we have a little bit more than just a line. We have a two-dimensional object. And then when we come to the x, y, and z, we get things that look like this. All right, what we have been doing the past couple problems is something like this. All right, so what happens here is we get one answer where all three of these planes meet. The purple, the yellow, and the blue. They meet right there at that one point. Some equations we have, when we have a system of three equations, we have the blue, the yellow, and the purple, three different equations, and they meet here at this line right here. How many solutions are there? There's an infinite number of solutions here that work. Any point on here is part of the yellow, blue, and purple planes. When we have, which we'll get into these in a minute, when we have ones like this, this one and this one intersect here on this line, the blue one and the purple intersect here on this line, but the yellow and the purple do not intersect. So therefore there's not one set of numbers that is on this line, this plane, and this plane. So because that's true, there is no solution. There are no numbers that work. Okay? So no solution, infinite solutions, and one particular solution there, which is what we have been doing. All right, so there will be some times where you will run into an infinite number of solutions, and sometimes that you'll run into no solutions. All right, so for example, and we did this earlier, gosh, I don't remember off the top of my head exactly what section that was that we did that, but when you got something like 6 equals 0 for your solution, that meant there was no solution. But if you got 0 equals 0, that meant there were an infinite number of solutions. And that's the same way with this here. Okay? So, if you're plugging away and you get something really psycho like this, that means there's no solution to the thing. You might as well stop. If you get something like this and your variables disappear, that's okay. You just write down infinite number of solutions. If you get numbers, like we did in the last two examples, that means that you have one point that works. All right, so that's pretty much what we're doing there. So this is pretty much what it looks like when you're solving. I'm not going to do the whole solution thing. I'm just going to show you what you'll run into if you get an infinite number of solutions and you know to just stop. Okay, so let's say that they give you this problem. Okay, so they give you that problem, and you go ahead and get rid of all your stuff, and you find out, oh, my top one already has a 1 in front of the x, so I'm good to go there. I don't need to do anything there. You go ahead and eliminate this x, eliminate that negative, and you end up, once the dust clears, with this for your numbers, and things are going well, and you go and do the next one, and you get 0 plus 0 equals 0. Okay. What happened is your y's and your z's disappeared and became zeros, and now you have a bunch of zeros. That means we have an infinite number of solutions, and you just stop there. Okay? Another thing you're going to run into is, let's say that you are doing some problems and you get something like this. When you're plugging away, you've reduced it down to a 1 in front of the z. You've got a 3y minus 11z equals 15. You know you still have some work there because that needs to be a 1. But down here on the bottom, somehow you've got this. That's an untrue statement. So right there, you know you have no solution, so you're done. You don't have to worry about making that a 1 or doing anything. Your x, y, and z's disappeared on the bottom, and your answer here does not work. So therefore, you have no solution, and you stop and just write no solution. Okay, so you can look at example 4 and just kind of look through that one. It's kind of a unique problem. You will not be tested on an equation like that, but at least look at it and see what's going on there. And it has to do with what x, y, and z are depending on the equation. Okay, so if you're purchasing a certain number of cars, your answer is going to have to be a positive number, so that eliminates some values and just gives you an idea of what is necessary in the answer depending on what the particular problem is. Okay, so you can eliminate some options for x, y, and z because of the problem rather than because of the way the system of equations works. So go ahead and look at that, and that's it for 7.1.